Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're going to continue talking about probability and specific the concept of conditional probability, okay? It's got a fancy sounding name. If I had to choose a subtitle for this, it would be the multiplication rule of probability. Last section, we had the addition rule of probability. A lot of times you'll hear this called the multiplication rule of probability, okay? So if you want to just do a quick review, in the last section, we were talking about the probability of two events, A or B. What is the probability of A or B occurring? And we found out that we add A plus B minus the intersection of the two. That's what we talked about in the last section. In this section, we're going to be concerned with probability of A and B. The two events happening, what's the probability of two of them occurring at the same time? Okay, and so we're going to look at two different events, and we're going to look at both of them basically occurring at the same time. So just to kind of give you a little bit of motivation, I'm going to draw kind of a little bit of information off the last section and apply it to this section. I think it's going to make it easy for you. In the last section, we were talking about the probability of A union with B, which is basically or. Okay, A or B or both. Okay, and we found out that that was the probability of A plus the probability of B minus the probability of A intersected with B, which is A and B. Okay, that's something you can go off and look in the last section and remind yourself of, okay? So, you know, we were drawing Venn diagrams in the last section with A and B, and there was a little intersected region, but what we were trying to find was the A or B, so the whole thing's shaded all the way across. That's what we were trying to find, and that's what that thing actually calculates. Now, notice what we were doing is we were basically adding the two probabilities together, A or B. We add them together because we're trying to make the total probability higher. If you have two events that can occur, and now you're trying to, like pulling out of a deck of cards, you pull an ace or you pull a king, well, if I'm looking at A or B, the total probability should be higher than either one of the events A or B, because now I'm looking at either or. So the probability should be higher. So I'm adding them together to make the probability higher, okay? Now, hold that in your brain, because now we're going to try to find the probability of A and B. A and B. Okay? We were doing this some in the last section just by using our logic, but now we're going to be a little bit more rigorous about it and say, well, I have event A and event B, and I want to know what's the probability of both of them happening at the same time. And if you just think about it for a second, whereas before, when I was looking at A or B, the total probability of those two things should be the sum of their individual probabilities, because you're really making the probability higher when you have two events and you're looking for either or. But now, if I have two events that can occur, and I'm interested in the probability of A and B happening at the same time, it kind of makes sense that the total probability should be lower. Because now I have event A and event B, and it's not good enough for A to happen by itself, and it's not good enough for B to happen by itself. They both have to line up and happen at exactly the same time. So the total probability of those two things ANDed together should be lower than their individual probabilities, because now I'm putting the constraint on both of them having to occur at the same time. How do you do that mathematically? How do you make the probability smaller? Well, we're going to multiply them, okay? The probability of A times, I'm going to write something down, don't freak out, I'm going to explain it to you. The probability of B given that A has occurred. That's what this notation means. I'm going to come back to it in a second. Basically, you have the probability of A and the probability of B, and you're multiplying it. Now, don't forget, probabilities are fractions. All of them are fractions. I mean, unless you have 0 or 1. Pretty much any probability in the middle is a fraction. So, if I have 1/2 times 1/2, I get a smaller fraction, 1/4. And so on. So by multiplying the probabilities together, I'm basically driving the total probability of down. Of those two things ANDed together, I'm driving the whole thing down compared to the individual probabilities. So before, when I was A or B, I add them together because I'm trying to make the probability higher, because I have two events, either one of which can give me a success. Here, I have both events that must occur at the same time to give me a success, and so I'm going to multiply those probabilities. That's going to drive the probability down, okay? Now, we need to talk about what this means. The way you read this is the probability of B given that A has occurred. It's very important that you understand this, because you can look at what the probability of A is, and you can look at what the probability of B is, but it's very important that you take into account the fact that A may have occurred, okay? I'm going to give you, we're going to do a lot of problems like this, okay? So if this doesn't quite make sense now, we'll get to it in the problems, but this is basically called conditional probability, okay? You have event A that's going on, and then event B may come after it, okay? And so what I need to make sure and realize is that event B is dependent in some cases on if A has happened. The easiest way to explain that is if you're pulling cards from a deck, okay? Have a deck of cards, and the probability of event A could be pulling an ace. Well, I take that ace out, let's say, and I toss it away, and then I choose another card from a deck. Maybe I'm looking for event B. Event B could be getting a king, okay? Well, the probability of B has now effectively been altered because I've taken the first card from the deck, and I've thrown it away. Now I have less cards in the deck. So usually your probabilities for cards, it's like something over 52, right? Because you have 52 cards in the deck. But if I take that first card that I pull and I throw it away, well, now I only have 51 cards in the deck. So I have effectively altered the probability of B, because probability of B usually would be divided by 52, but because A has occurred, I have really and truly altered what the probability of B is. So when I'm using this thing, I always need to do the probability of A and multiply by the probability of B, but just in the back of your head, you have to take into account the fact that A has occurred. This is really easy to do when you're doing the problems. Just when you're calculating the probability of B, just try to think to yourself, has the event A actually altered the probability of B? And if so, go ahead and take it into account, okay? So just to kind of write that down, an example of conditional probability, if the probability of A is to draw an ace from a deck, okay, then that would be 4 out of 52 cards, right? Because there's 4 aces out of 52 cards. So it's 1 over 13. That would be the probability of A, let's say. The probability of B, let's say I draw this card and I throw it away and I don't replace the card in the deck. So I may want to draw for event B a king without replacing this ace. So then we know there are 4 kings in the deck, but there are no longer 52 cards in the deck. There's now 51 cards in the deck. I have altered the probability of B. I have altered the probability of B because I have removed one of these cards. If I had just tried to calculate the probability of drawing a king just by itself, it would be 4 out of 52. But because A has happened, I have altered the probability. Okay, 4 out of 51, because the ace is gone. So these two things are said to be dependent events, or you could say B is dependent. The probability of B was dependent upon the probability of A. They're dependent events. They're linked somehow, because the event A that has occurred basically influences event B. Okay, and this is sort of the easiest way to talk about this. Now, in the books, you'll see a lot of times that you can have event. Drawing on this a little bit more, event A and event B are independent events if the event A does not influence event B. Okay? So we've talked about dependent events. These are what are called dependent events. When the second event occurs and the probability is altered because of the first event. But if A and B are independent, it just means that A does not influence B at all. And how could that happen? If event A was to flip a coin to get a heads, okay, and then event B was to flip the very same coin to get a tails. Okay, to flip a coin to get a tails. You know, just from thinking about this, you have a coin, you flip it as many times in a row as you want. The fact that I flipped it and got heads the first time has nothing at all to do with the fact that I may get tails on the second flip. So A does not in any material way actually influence event B in any way at all, because you're not removing anything from the system. You're not changing anything. So these things are called independent events, okay? So for independent events, the probability of B given that A has occurred is really just the same thing as the probability of B all by itself, because there's no difference. The B given that A has occurred is exactly the same thing as B, okay? So when you're writing your probability multiplication rules, the probability of A and B, okay, go all the way back up here to the top. A and B is the probability of A times the probability of B given that A has occurred. You can, somewhat simplify this and just say now it's the probability of A times the probability of B. You don't have to write probability of B given A because they're independent events. A has nothing to do with B, so just A times B is perfectly fine. Now again, I prefer just to always use this one up here, way at the top. I prefer to use that one because it's always going to give you the right answer. If you're looking for two events, A and B, and you're trying to figure out if they can both happen, then you look at the probability of A happening, multiply it by the probability of B given that A has happened, and in the course of the problem you'll figure out if A has any influence on it or not, and then you just multiply these two together and you get the right answer. So the thing to really pull out of it really is when you're taking the probability of two things ORed together, you're adding them together to get a bigger probability. When you're trying to find out if two things are ANDed together, they both occur, you're multiplying them together. And the only thing you have to know is that whenever you're looking at that second event, just look at it to try to take into account when you're looking at that probability, see if event A influences it in any way, and if so, you just take that into account and you're good to go. So at this point, we need to solve some problems because this kind of thing is not going to come to you and be your best friend just by thinking about it. You have to work some problems, so let's do that here. If you were born on June 15th, okay, what is the probability that two of your friends will also have the same birthday as you? So my birthday is June 15th, let's say, and two of my friends come into the room. He has a birthday and she has a birthday, and I want to know what are the odds that both of them have my birthday, which just happens to be a certain day of the year, June 15th. So just like I start all of these problems, the first thing you do is you write down your events. Event A, your friend has a birthday on June 15th. Friend has a birthday on June 15th. Event B is your other friend, these are two different friends, has birthday on June 15th. Okay, so those are my events. So what I'm looking for is the probability of A and B. This is AND. So the way I do it is I say the probability of A times the probability of B given that A has occurred. Okay, the probability of A has occurred. So let's calculate this. What is the probability of A? What is the probability that your friend has a birthday on June 15th? Well, there's only one day called June 15th out of 365 days. So the probability of A is 1 out of 365. The probability of B, given that A has occurred, what is the probability that your other friend has a birthday in June 15th? And that is exactly the point when you look at it and you say, okay, the second friend, does my first event have anything to do at all with that second event? In this case, the answer is no. The fact that your first friend has a birthday on June 15th has nothing to do with the fact that your second one may have a birthday on June 15th. So there's really no dependence here. So I just write 1 out of 365 again. Because your friend birthday has exactly the same probability of occurring. So I always use this general formula, even though these are independent events and you really don't need to write this bar A here because it's not a dependent event. I always write it because it helps me remember to check. Okay? So 1 over 365 over 1 over 365 is 1 over 133,225. Okay, which is 0.00000075. Very, 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 very small number, almost zero. The odds of two people having the same birthday, any two random people having the same birthday, very, very small number. Okay, so again, probability of one event times probability of the second event. You just have to make sure the second event takes into account the first event. Okay. The second problem says you flip a coin and then you also toss a single die onto the table. What is the probability that you get tails for your coin toss and you roll a 3 in the die? So again, it's two events. tossing a coin, rolling a die. What's the probability of getting a tails on the coin and a number 3 on the die? Okay, so same thing as always. I label my events. Event A is that I get tails, and event B is that I get a 3 on the die. Okay, so again, I'm looking for the probability of A intersection with B, which is A and B. Okay, so it's going to be the probability of A times the probability of B given that A has occurred. Given that A has occurred. Okay, so what's the probability of A? What's the probability of throwing a tails? 1 tails out of 2 sides of the coin, probability is 1/2, times. What is the probability of rolling a 3 given that A has occurred? And again, you look at it and you just think about it and you say, well, I'm rolling a die. That action has nothing to do with the fact that I tossed a coin. So there's really no dependence here. These are independent events. But it just reminds me to check. Okay, the probability of rolling this 3, there's 1 3 on the die divided by 6 total positions on the die, so it's 1/6. Okay, so the answer is 1/12. 2 times 6 is 12, and so you do that in your calculator, 0.083. Usually you leave it as a fraction, but I'm just kind of converting it to show you. It's a pretty low probability. Probability of 1/12 of getting a tails and rolling a 3 on that die. Okay, the next problem says you draw a card from a 52 card deck. You then draw a second card without replacing the first one that you drew. Okay, what is the probability of getting an ace on the first draw and then a king on the second draw? And right away you should be able to see that these are dependent events because event A is pulling the ace, but I do not replace that card from the deck. So event B, which is drawing the king, is influenced by A occurring. Okay, so the first thing we do is we write our events. Event A we're going to say is drawing the ace, and event B is drawing the king. Okay, so what I'm saying is that these are dependent events because I'm not replacing the ace before I pull the king. Let's see if that makes sense. The probability of A intersection with B, which is A and B, is equal to the probability of A times the probability of B given that A has occurred. That's what that means. Okay? What is the probability of drawing an ace? Drawing an ace is 4 out of 52 because there's 4 aces in the deck of 52 cards. Times. What's the probability of drawing this king given that I've already drawn this ace? Well, there are 4 kings in the deck, but there are no longer 52 cards because I pulled the ace. Now there are 51 cards. So you see this probability has been influenced because of this event occurring. And that's exactly what that means. So that's why it changes. That's why you have to write B bar A. That means B given that A has occurred. So what you're going to have is 16 on the top over 2652 on the bottom. And that's going to reduce to 4 over 663. And on your calculator, you can write that as 0.00603. That is the probability. So again, the probability of the first event was 4 out of 52. The probability of the second event was influenced because there are now less cards in the deck. Once you know that, you multiply them together and go from there. So really the thing to do is for every other event that happens after the first one, you just have to make sure that you're taking into account the fact that the first one has happened. Okay? The next problem says, Jason, Jamie, Sarah, Jill, and Scott, 5 people, arrive at a party randomly and at different times. Okay? What is the probability that Jason arrives first and Scott arrives last? Okay? So again, there are 5 people at a party, Jason, Jamie, Sarah, Jill, and Scott, 5 people. What's the probability that Jason arrives first and Scott arrives last? And I think you'll see, especially when we write it down, these are also dependent events because once Jason arrives first, I've effectively removed one of the people from the list that can arrive last. So because I've actually arrived first, okay, I've removed myself from the list of people that can arrive last because I'm already at the party. So these are dependent events. These are not things that are totally unrelated to one another, and that's what you just have to get the hang of. Event A, let's say, first thing we're going to do, Jason arrives first. Okay? Event B is that Scott arrives last. And I'm claiming that these two are dependent events. Let's make sure that this is the case. The probability of A and B happening, okay, is going to be equal to the probability of A times the probability of B given that A has actually occurred. Okay? So let me ask you this. There's 5 people here, Jason, Jamie, Sarah, Jill, and Scott. What's the probability that Jason arrives first? Well, there's only one way that can happen. Jason is the guy that arrives, divided by the 5 possible people. If they arrive randomly, there's 1/5 chance Jason will arrive first, times. What's the probability that Scott arrives last? Well, again, there's only one Scott, so there's only one way that that success can happen, divided by how many remaining people can arrive last. Well, there's only 4 more people left, because if I've arrived at the party, then there's only 4 people left to possibly arrive last. So the probability of Scott getting last, given that A has happened, is 1/4. Because I've been removed from the pool, there's the probability of B happening is actually changed as a result of A happening. Okay, because there's less people involved, so that's why these are dependent events, okay? So the answer, now that you know that, is 1/20. So just like everything else in this class, I mean, the math is simple. I mean, you're not going to get math any simpler than that, except in 7th grade. But the trick is knowing what to do, and knowing that these are dependent events, and knowing how to set your probabilities up, and that actually is very, very difficult to do. The only way you get good at it is to work problems. The only way you get good at it is to work problems. Let's continue doing that. Find the probability of getting 8 heads in a row with a balanced coin. So flip a coin, flip a coin, flip a coin, flip a coin 8 times. I want to get heads, 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 heads 8 times. How do I do that? Well, this is a little bit different because I have 8, effectively 8 events, okay? Event A is getting a heads. Event B is getting a heads. C is getting a heads. D is getting a heads. E is getting a heads. F is getting a heads, and G is getting a heads. 1, 2, 3, 4, 5, 6, 7. Still not done. E, F, G, H is getting a heads. Okay? Now, my question to you, this is flipping a coin. So all of these are independent events. Okay? They're just not dependent on another. If A happens, it doesn't influence B at all. Okay? So what we need to do, what I'm showing you this problem for, is to kind of show you by example that the probability that you're going to write down here, okay, let me write it under here. The probability that you're actually interested in is the probability of A happening and B and C and D and E and F and G and H. So all I'm trying to show you here is this rule that we've been talking about, this probability rule, where you have A and B and you multiply them together. It can be extended to as many events as you want to have happen as a success, okay, in your experiment, okay? Because they're independent events, nothing is really, no event here is dependent on any other event, so this is just going to be equal to the probability of A times the probability of B times the probability of C times the probability of D times the probability of E times the probability of F times the probability of G times the probability of H. Okay? Probability of H. 1, 2, 3, 4, 5, 6, 7, 8. And, you know, in each one of these, you really don't need the bar given that anything else has happened because it doesn't matter. They're all independent. They're not really going to affect anything. So, what's the probability of A happening? Probability of getting a heads is 1/2 times 1/2 because the second event, getting a heads, is also 1/2. Doesn't affect anything, the fact that the first one happened. 1/2, 1/2, 1/2, 1/2, 1/2. 1, 2, 3, 4, 5, 6, 7 events, 1/2. I think I have 8 events here, and when you multiply all this together, you get 1 out of 256. Okay? So what this is saying is that if you perform this experiment, there's 1 out of 256 times that this experiment is going to actually be a success. Very low odds that you're going to get 8 heads in a row. Okay? Very low odds. Okay, the next problem says, find the probability of getting 3 3s, then a 4 or a 5 if you roll a dice 4 times. 4 rolls of a dice. So, roll a dice, roll a dice, roll a dice, roll a dice. 4 times. Okay, what I want to find the probability of is I get a 3, 3, a 3, And then on that last one, I can get a 4 or a 5. That's exactly what I'm trying to do. So let's label our events. There's 4 events going on here. First event is getting a 3. Second event is also getting a 3. Third event is also getting a 3. Fourth event is getting a 4 or a 5. Okay, 4 or 5. And these are independent events because these are just rolling dice. The fact that I get a 3 on the first one has nothing to do with getting anything on any of the other ones, so they're independent. So the probability of A and B and C and D is just going to be equal to the probability of A times probability of B times probability of C times probability of D. And there's no bars in here because there's no dependence on anything else happening before. You don't really need them. As long as you make sure and check for them, that's okay. All right? So the probability of A happening, what is the probability of getting a 3 when I roll the die? Well, there's 1 3 on the die, and there's 6 total sides, so the probability is 1/6. The second time I roll it, again, probability of 1/6. The third time I roll it, again, the probability of 1/6. Fourth time I roll it, now I'm trying to get a 4 or a 5. A 4 or a 5. Now this goes back to the section right before this. What's the probability of 2 things or together? You add them up. The probability of getting a 4 is 1/6. The probability of getting a 5 is 1/6. So I'm going to add them up to give me the total probability of both of them there. Now you don't have to do any subtraction here. You know, usually the probability of 2 things added together is A plus B minus the intersection of the 2, like we did in the last section, but there's nothing like that here because when you roll a dice, there's no commonality between these two. These are mutually exclusive events. You get a 4 or a 5. You can never have both, so there's nothing to subtract like we were doing before. So literally, you take one probability and you just add it to the other to find how to when you have those things or together. And because that is my last event, I need to multiply the result by all the other ones. So 1/6 plus 1/6 plus 1/6, 1/6 times 1/6 times 1/6 is going to be 1 over 216 times, on the inside here, I'm going to have 2 over 6 here, which is going to be 1/3, okay? Over here, 2, 6, which is going to be 1/3, and you do this multiplication, you're going to get 1 out of 648. So again, the math is easy. It's just figuring out what to do. First event, second event, third event, fourth event was tricky until I realized it was an OR, and I knew I could add these probabilities together. Each one is 1/6, and then you just do the math, and you get the probability of 1 out of 648. Okay. Now, the next problem says if, and this is kind of a little bit odd kind of problem, if the probability of event A is 0.8 and the probability of C is 0.35, I want you to find, and the probability of A and C, or A intersection C, is 0.28. Are these 2 events independent? Are these independent events? Now remember what independent events mean. They basically mean that the one event does not influence any other later events, and what it also means, kind of from more of a math, kind of writing down point of view, independent events, if an event is independent, what it means is the probability of A and C is just going to be the probability of A times the probability of C. There's no probability of C given that A has occurred, because if they're independent, it has no meaning, because if A has occurred, it has no influence on if C has occurred, if they are independent, so there's no need to write that down. So basically all you're checking here is to make sure that the probability of both happening is the same thing as the probability of these 2 things multiplied together. So 0.28 was the probability of both happening, equals with a question mark because we're checking. Probability of A is 0.80, and the probability of C is 0.35. So we just need to multiply these things together. So 0.28 does indeed equal 0.8 times 0.35, 0.28. So they are equal, so yes, these are independent events because this had happened. If this on the right hand side multiplied to something other than 0.28, then we would know that these things were not independent. The probability of C is basically going to have been altered in that case because of the fact that they were dependent events, if it in fact didn't multiply out to give you 0.28. It's kind of an odd little problem, but it's the kind of problem that you might see on a test, especially at the beginning, just to kind of see if you understand what the definition is. Instead of asking you, what is the definition of independent events, they might just give you a few probabilities and see if you can apply the definition. Okay. The final problem that we're going to have is a couple, parents, are planning to have 5 kids. Okay. What is the probability that there will be at least one girl among their 5 kids that they have? So they're planning to have 5 kids. What is the probability that they're going to have at least one girl? Now this is very similar to what I was talking about before, when you have to really read the words and really understand what it's asking you and do a little mental gymnastics sometimes to solve the problem. And this is one of those cases I generated here to show you that, okay? So when you see the phrase at least, when you want at least this or at least that, you really probably are going to end up having to rewrite that in some way to make it easy for you to calculate. So let's do that. So the key to this problem, the key to making sense of this problem, okay, because you know it's going to be a problem here involving multiplication in some form or way, but the key to it is that when you have the phrase at least one girl, when you have that phrase, okay, what you need to convert that to is one or more girls. And that may be something automatic that you do in your head. You need to think about that, internalize it, make sure you understand that means one or more girls. So our event A is going to be that the couple is going to have one or more girls. Now, given the tools that we have, knowing that they're going to have 5 kids, knowing that they want one or more girls, there's not really an easy way to solve this problem given the tools that we have. But, so I'm going to teach you kind of something I want you to look for. If on the test you have a problem like this where at least this or at least that, try this trick, it'll probably work, okay? What I'm going to do is define, here's the event A, one or more girls. I'm going to define the event A complement, which means all other outcomes other than A. Or in other words, everything opposite of A. That's what complement means. The complement of A means no girls. Think about that for a second. It's very, very important. If the event A is having one or more girls, then the complement of A, which is, quote, the opposite of A, is having no girls at all. Okay? One or more girls means I have some girls in my kids, but if I have A complement, which is sort of the opposite, I have no girls at all, which means that I have all boys. If I have no girls, I have all boys. Okay? So now, instead of finding the probability of A, I'm just going to go ahead and try to calculate the probability of A prime, because I believe that's going to be easier to calculate. What's the probability of A prime? If I'm going to have 5 boys, okay, if the odds of getting a boy versus a girl is 50-50, 1/2, the probability of the first boy is 1/2, probability of the second boy is 1/2, third, fourth, and fifth. Okay? I can't write this time. Okay? So I have first kid, second kid, third kid, fourth kid, fifth kid. Each time the probability here of getting a boy is 1/2. So the total probability of getting all boys is very low, okay, given by this. So the probability of A prime is going to equal, when you multiply all this out, you're going to get 1/32. Now you may be asking me, why did you do that? I'm not even looking for the probability of all boys. I'm not looking for the probability of A complement. Why would you do that? Well, you need to remember that the probability of A is always going to be equal to 1 minus the probability of A complement. So now I know what that answer is. I can do that and I can find what I want. 1 minus 1/32 is equal to, changing this 1, 32/32 minus 1/32 is equal to, doing the subtraction, 31/32. That is the answer, 31/32. And this is very, very close to 1. So the probability of A, my event A, and A, by the way, was getting at least one girl, or one or more girls. That's what I was trying to do to begin with. The probability of having at least one girl is very, very high. And that's just a simple matter of kind of like flipping the coin. I mean, if the probability of each event happening is 1/2, then if you do 5 times in a row, the odds of getting one of those things is going to be at least one of those things is very, very high, okay? So it's kind of I hate to say it's really a trick, it's just something to look for when you see these kinds of problems. If you see at least, find the probability that there will be at least, then a lot of times what you'll have to do is define the event and then define its complement. Okay, and usually finding the probability of the complement's easier, because if I have one or more girls, meaning that's my event, a complement is having no girls, which is all boys. It's very easy to find the probability of all boys, all 5 boys. That's very easy to do, and I can find the complement and then find the answer. So in this section, we've covered quite a bit of ground. We've covered the conditional probability, basically, which is the probability of 2 events happening, A and B. The last section we did A or B. We added the probabilities together, basically to get a larger probability. This section, when it's A and B, we multiply the probabilities together, effectively driving the probability down. Because if 2 events are going to occur, the total probability of both of them occurring is going to be less than each individually, because I'm imposing that requirement that both must occur. So the odds are going to be lower. The probability is going to get lower. And while you're doing, the most important thing that you do when you do this rule, you look at the probability of A times the probability of B, but you have to factor in the fact that A has occurred. Probability of B given that vertical bar that A has occurred. Some of the problems, you'll have these independent events where it won't make a lick of difference if A occurred or not, and you'll just you go about your business and calculate the probability, and that's fine. Some of the problems, when you're removing cards from a deck and you're not replacing them, you're actually influencing the probability of B occurring, and you need to factor that into your probabilities when you're doing this. And when you do that, you'll have a bulletproof way of finding the probability of A and B occurring, otherwise called A intersection with B, is the probability speak way of actually saying probability of A and B occurring.